Good afternoon, everyone. This is Mr. Couple. Today I'm joined with my IB Physics HL Year 1 students. Say hello if you're in chat.
Hello.
Hey,
It's Braden and
hello.
Robert. Was that Alberto? Or was
That
that?
was
No, that was Eddie.
Eddie.
What's up, Eddie?
Yeah. Hey.
All right, so today we're going to be looking at an extension really of what we talked about last week, which was the double source interference. And we'll be kind of combining diffraction and double source interference together to create what we call double slit interference. So we'll be looking at that today. You guys might remember that I mentioned that diffraction and interference are kind of the same thing. And so you'll be seeing a little bit more about that today, how diffraction and interference go hand in hand with each other. The three main ideas for today's lesson are number one, that interference for light was first discovered in 1801 by Thomas Young. Number two, light passed through a double slit creates a pattern of interference fringes. And then number three, you can determine the wavelength of a wave from the fringe spacing. All right, let's begin with a pretty famous story in physics. So there is this battle that sort of raged in the 1600s about what is light. So there was one side, which was Christian Huygens, and Christian Huygens said that light is a wave, and that could explain all the different behaviors of light. And you'll remember the Huygens-Fresnel principle that we talked about last time with the little wavelets. That was Huygens. So Huygens is coming down on team wave, and on the other side is Isaac Newton, who's the one that discovered the spectrum of light. And Newton proposed a corpuscular theory of light, which is that light is a particle. So what they're both trying to explain is why does the refraction of light, of sunlight, why does it spread out into all the colors of the rainbow? And that's what Isaac Newton discovered that. And that's where you get the Roy G. Biv from. So that was a discovery made by Isaac Newton. So Newton said, oh, the reason why the light spreads out the way it does is because light is made of particles, and he called them corpuscles. And every particle has a different size depending on its color. And so that's why the red and the purple light will bend differently, and then they'll get spread out when they go through a prism. Huygens said, no. The reason why the light spreads out differently is because there's different wavelengths of light, because light is a wave. And so the different colors have different wavelengths, where red has the longest wavelength, so it doesn't bend as much, and then purple is a shorter wavelength, and so it bends more. And so they kind of just went back and forth and argued and argued. The problem, though, is that the proposed size of the light particle and the proposed length of the wavelength was smaller than any of the current equipment could measure. And so they are both sort of never going to resolve this debate. It was a philosophical debate. They had no evidence, experimental evidence, to sort of turn it into science. The evidence wasn't found until about 100 years later. In 1801, this dude, Thomas Young, who's a British physicist, he came up with the double slit experiment. So the basic idea is you shine light at two slits and you look to see what pattern are you going to see on the screen. And so this is a really elegant, awesome way to decide whether light is a particle or a wave. It's a really cool experiment. It's famous in physics. So here's the idea. If the wave theory is correct, when the light from our source comes out and hits these slits, the light will diffract, and then you'll have this interference pattern that forms on the screen. So you have some areas of constructive interference along with areas of destructive interference. And so you'll get this interference pattern that forms on the screen. But if light is a particle, then the only particles that will make it past this barrier are the particles that can slip through the cracks here. And so you'll notice a really bright beam at one spot representing the particles that went through this slit, and you'll get another bright beam at the other spot representing the particles that went through the other slit. You won't see this interference pattern. So if light is truly a wave or a particle, then one of these two outcomes is going to be observed. And so Thomas Young was the one who figured this out, and he performed the experiment, and here's what he saw. So I'm going to show you a modern reenactment of this experiment using a laser beam. So down here, those are the double slits. They're really, really small because remember that the wavelength of light is on the order of, 400 nanometers or so. 400 being probably like green, I think. But anyway, you're really, really, really small, just hundreds of nanometers. It's incredibly tiny. And so you'll remember that diffraction only occurs when the size of the slit or the aperture is roughly equal to the wavelength of the light. So this is a very, 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 very tiny slit. And so you can see that the technology in Newton's time, and Newton-Huygens at their time, the technology didn't exist to manufacture things at this scale, at this size scale, where it took about 100 years of technological development before someone could figure out how to do it. And sure enough, when you shine the light through the double slit, you see an interference pattern. So you can see it there. It's kind of pixelated and gross, but here are some higher quality versions on the right-hand side. And the one thing that's kind of cool to notice is that the spacing between these is dependent on the wavelength. Where with green light, so red light has a long wavelength, whereas green light has a shorter wavelength. And so you can see that the shorter the wavelength is, the shorter the separation between the fringes will be. So that's proving that light is a wave, or rather, we should say that light exhibits wave properties. Because as you know, or maybe you don't know, but light is actually not a wave. It's actually particles called photons that act like waves. So we could say that light exhibits wave properties. It's this whole thing in quantum physics. We call it the particle wave duality. We'll be studying more about that as we go through this class. Do you guys have any questions right now about any of this before I move on? So we're good. I feel like I'm not recording. I'm just going to check real quick, make sure I'm recording. Yeah, I'm recording. Okay, good. I don't know why I thought I wasn't recording. Okay, so I wanted to show you guys something here. So last class we talked about single slit diffraction. So single slit diffraction happens where the edges of the barrier act like two sources of waves. And so you have like two wave sources coming out from here, and then they interfere with each other, creating this interference pattern. We have like this really bright constructive interference in the center, and then you have like some more constructive interference out here as those waves sort of bend out to these extreme places. But the thing is that the further it spreads, the less the intensity gets. So you just see this like really big like bomb in the center for a single slit diffraction. But now with double slit diffraction, you're going to end up with sources here, here, and here, and here. So you're going to get this much more complicated pattern. So you can see that the single slit envelope, we're calling that the single slit envelope. You can see the single slit envelope is still there. This is a graph of intensity against position. The single slit envelope is still there, but there's these large variations within it. And so you're having like double interference. So like each slit times two slits. So one slit creates this interference pattern, and now you're multiplying it by another slit, and so you get this crazy pattern. And you can really clearly see that in the images up above, where there's this deep dark spot there, bright, super high intensities there. And so that's what we're seeing is like these really high intensities here. Whoops. These really high intensities in the center giving rise to these smaller intensities off to the side. So you get this very complicated pattern, and you don't really need to know you don't need to know the equation that describes it or anything like that. But there's one thing that you need to be able to do, and like all that IB wants you to be able to do is to calculate the distance from the central maximum to the first maximum. So you want to find this distance there, and we usually call that S, and it's called the fringe spacing. So S for spacing. That's all that you need to be able to do, is to calculate the fringe spacing. And here they are side by side. So when you have a single slit, you just see that big bonk, like bright spot in the center, whereas with the double slit, that big bright spot in the center is still there, but it's split up into these smaller fringes. And we just want to be able to figure out how far apart those fringes are. Here's another picture just to make it 100% clear. So we talked about last time with the double source interference over here. This is the double source. So double source interference. So we're really looking at this area over here. And so you can see like those minimum and maximum lines, the red and black lines over here, showing the different path separations. And so I just want you to remember that we're looking for areas of constructive interference, which is where it's bright. So the bright spots happen where you have an integer multiple of wavelengths. And then the dark spots happen where you have a half integer multiple of wavelengths. So just remember that from last time, because we're going to need to use that in a little bit. Oh, everything's disappeared. Okay, so we're going to look at this picture. This is out of the textbook. And so what we need to do is we need to determine an expression for the fringe separation. So remember, once again, from that central bright spot to the center of the next one, we want to find that distance. So it's right there. It's represented with S. So we're trying to measure how far apart the fringes are. What do we know? So we know the wavelength of the light is lambda. We know the distance between the two slits is little d. And then the distance to the screen is big D. So I'll just remind you guys, I probably should have put this picture on right here. So our distance to the screen, that's big D, The distance between the two slits is little d, and then it'll create the interference pattern on the screen. Looks something like this. And we want to find the spacings between the two fringes, like that is the little s. And so that's basically what we seek an equation that does that. All right, this is a very complicated derivation, and the IB does want you to be familiar with this derivation. Of course, you're not going to be able to you don't have to recreate the derivation, but they do want me to show it to you. Okay, one of the big assumptions we're going to make is that the distance between the slits, so that's what this is over here. These are supposed to be the two slits. The distance between the two slits is negligible, so negligibly small compared to capital D, the distance to the screen. So the distance to the screen is right there. That's going to be capital D. And so we are going to say that little d is much, much smaller than big D. Okay, so what we're going to do to figure this out is fairly complicated. So we know that the reason why interference occurs is because of a multiple, what am I trying to say? The waves have to add in phase. So they have to arrive at the same point in phase, and then they'll constructively interfere with each other. So we're going to say that right there, that's the first bright spot. So we'll have the big bright spot there, and then this is the other bright spot here. And so we've already got a variable defined for that as being s. So we want to figure out what that s is, the distance between the two. So now what we know is that the wave from here is going to come out and hit that spot, and the wave from here is also going to come and hit the same spot. And they're going to have to reach that spot in one way lambda. So like the extra distance. So let's call it the path difference. So we'll call it p. So we know that for this first one, the path difference is just going to be lambda. If you want to go out to the next one, to here, the path difference would be 2 lambda. Whoops. And so on. So each one of these fringes is happening, the bright spots are happening where the path difference is more and more. So the first one that we're looking at is just 1 lambda. So we're trying to find that first spacing, which is just the path difference, is just going to be lambda. And so you can see here that there is a path difference. So imagine that this is a ray of light coming out this way, and there's a ray of light coming this way. And so we can find the extra distance by dropping down a perpendicular. So I'll do that right here. So if we drop down a perpendicular here where this is perpendicular, then this distance right there, that's p. That's the extra distance that the light from the bottom slit has to travel compared to light from the top slit. And so what we know is in order to get a maximum at this point here, that p has to be lambda. So I'll just put that down here. So that p is going to equal to lambda. And so that's what we know for the first path. Now, if I move this up to the next one up, then that extra distance would increase to 2 lambdas. But we're just looking at the first fringe. All right, so now what we need to do is do a little bit of geometry and search for what are called similar triangles. And so the way we're going to do that is by setting up for searching for 2 triangles. I'm going to see if I can do ink to shape on my surface. So if I go like this and like that, I'm trying to make a right triangle. Is it going to do it? It's not doing it. Let me try one more time. Is it not recognizing it as a triangle? Let me try it again. There we go. I got it finally. Okay, so that it does. I don't even like how it looks. Whatever. I'm done. Okay, so we're going to look at this center point here. Now, the first question it's really interesting to ask about is how is it if light is coming through here and light is coming through here, how could light actually reach the center of the screen? And that's a really weird thing to think about. So like you would imagine that light would just keep going straight or here, but it doesn't, right? It actually hits the center of the screen. And so the reason why is because of interference. So light is a wave, so it's going to diffract through this opening, and it's going to diffract through this opening, and it's an equal distance that it travels to those 2 spots. And since the distance is equal, obviously, to the center, you're going to get constructive interference because they both travel the same path length, and so you're going to get a bright spot there, even though it's on the other side of that barrier, and it's on like it's not. What am I trying to say? It's like not. It's in the middle, like this part over here is blocking any incoming light gets blocked from reaching that part of the screen. But because it's a wave, it can diffract through the slits. All right, so what am I doing now? Okay, so we want to find the triangle. So the triangle that we're going to look at is this one here. and this one here. And the reason we're choosing that triangle is because it's a right triangle, first of all, and it has two of the quantities that we want. So we can say the tan of that angle of that triangle right there. So that's the angle. The tan of that angle is the separation distance, so opposite over adjacent. So it's that separation S divided by the distance to the screen. So that's the tan of that angle. The second triangle we want to look at is going to involve that path difference and the distance between, so this distance over here, D. So this is the second triangle over here. And you'll notice that it's also a right triangle. We're going to go from this angle here. And then from that one, the D is the hypotenuse of that right triangle. And then the path difference is the opposite to that. So for this one, we're going to use sine. So sine is the opposite, which is lambda over D. Remember, lambda is the path difference, the extra distance that it travels. Okay, so it turns out that these two triangles are similar triangles. And the reason they're similar is because they both have a right angle and they have that theta is the same. So you imagine like if you rotated this whole thing, like if you imagine like taking this picture and you just started rotating it, I can't rotate it, but imagine if you rotated it, then those two angles would rotate through the same angle. So they're congruent angles to each other. So when you have a triangle that has two angles that are congruent, well, they're triangles, so the third angle also has to be congruent, and then that means that they're similar triangles. So it means that the sides of the triangles are in proportion to each other. The second thing is, remember how we said that the distance between the slits was much, much, much smaller than the distance to the screen? The distance between the slits is near the wavelength of the light, which is nanometers, but the distance to the screen is a real life distance, like meters. So the nanometers is way, 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 way shorter than meters. And so what happens is that angle right there is going to be very, very, very small. So since D is much, much smaller than D, that means that the theta is going to be pretty much zero. It's going to be a very, very small angle because the distance here, imagine that you shrank that little d, you shrank it down really, really small and took that big D and like stretched it out really, really far, then you would realize that that angle is going to go to zero. Now here's what's cool. If you look at a graph of tan, so the blue line here is a graph of tan. So if you look at tan, and then we look at a graph of sine, so that's the red one, then what do you notice here at zero? So if you look at a graph of tan and sine, you'll notice that when theta is about zero, which is here, what do you notice about tan and sine? Anybody still in chat? You guys have been awfully quiet. No one's here. What's going on? Where are you guys? Where is everybody? Everyone's all quiet. What happened? Okay. Everyone's too shy to say anything. Well, anyway, you can see right here that they're the same. So when theta is really, really small, tan and sine are going to equal each other. So when theta is very, very small, tan theta is approximately equal to sine theta. So if we look back over here in our equations, we can say that, hey, this tan theta, it's basically sine theta. And so now these two expressions, we have two expressions for sine theta. So we can set them equal to each other. So that means that the fringe spacing divided by the distance to the screen, that ratio has to be the same as the ratio of the wavelength of the wave to the distance between the two slits. And then that's it. That's our double slit diffraction equation. What we want to do is solve this for the fringe spacings. So the distance between the fringes is going to be S. Solve this for S. We just multiply both sides by capital D. Multiply both sides capital D, and you get this equation which says lambda capital D divided by little d is the distance to the fringe spacing. So remember, this is the distance from the central maximum to the first minimum. So you're going to have the first maximum. So we're going to have that as your pattern. And so S just tells you the distance between those first two. That's it. So if it said like find the distance to the fourth maximum, you'd have to like count out and multiply it by 4. All right, here's an example problem to solve. See how much time I have. I got 10 minutes. You guys are seriously not there? Like, am I by myself now? This is really weird. Look at all these people in here, and they're all super quiet.
We're here.
Okay, thanks. I'm like making sure that my mic's not muted or something.
Quite frankly, I'm just scared.
Oh, you guys need to be more brave. We can't learn physics if we're scared. Okay, we're going to look at this worked example. This is very similar to a practice question I'll be giving you guys if you decide to do that option for your demonstrate your understanding. Okay, it says use the figure in this graph for this question. In a double slit interference experiment, the two slits are separated by a distance of 4.2 times 10 to the negative 4 meters, and the screen is 3.8 meters from the slits. Question A, determine the wavelength of light used in this experiment. So imagine, like back in that, where was it? I'll show it to you guys in the picture. So imagine like you have this laser and you're like, hey, I want to figure out what the wavelength of this laser is. Like I really want to measure the wavelength of red light. Well, I'll go into my shop and I'll machine, if you zoom in on this, it's basically like two little tiny slits that are side by side. So you can machine down how closely you want those slits to be. And you can measure that precisely with a mechanical device. Then you can get in there with a magnifying glass and you can measure how far apart that didn't work. You can measure how far apart those two spaces are. You can measure that with like a microscope or something like that. And then once you have S, so there's your S, you can measure out your D to the screen, and then you can measure out your little d between the two fringes, and then all that's missing is the wavelength. And so you can measure the wavelength of light using a double slit interference experiment, and using that equation we just derived. So that's what we're going to do with this data. So here's your experimental data over here. You've got a plot of the intensity as it varies with the distance. So just imagine that you took a little machine and you just went along the screen. So this is, where am I showing you up here? So like imagine you have your screen over here and you just take like an optical sensor and you just scan it along the screen. And then as it scans along the screen, it measures the intensity. And then it creates this graph. Question B, suggest the effect on the separation of the fringes of decreasing the wavelength of light. So what would happen if our laser was a shorter wavelength, like if we went from red to green? And then lastly, what's the feature on the graph that enables you to deduce that the slit width is negligible? All right, so let's do part A first. So the equation is quite simple. It's just the fringe spacings, S is equal to lambda, the wavelength of light, times the distance to the screen, divided by the distance between the slits, the slit distance. So what do we know so far from what's given to us? So it says two slits separated by a distance of 4.2. So that's what D is. So we know that little d is 4.2 times 10 to the negative 4. It says that the screen is 3.8 meters away. So that's big D. And remember that one of the major assumptions of our model was that big D was much, much greater than little d. And so you can see in this case, it is true, where our big D is 3.8 meters, it's way, way bigger than 4.2 meters. It's about 10,000 times bigger. So our approximation is going to work out, where we said that sine and tan are about the same. And what are we missing? So we've got little d, we've got big D. Oh, we're missing the wavelength, which is what it asked us to find. But notice that in order to find the wavelength, we got to figure out what S is. And so that's where the picture comes in, the graph over here. We can find S from this picture. And so realize that this first big peak here, that's our central maximum. And then we have the first maximum here, and the first maximum here, and then the second maximum, and then the third maximum, and so on. And that's what we're seeing with these peaks. Wherever the intensity peaks is a maximum where we have constructive interference. So how do we find S? So S is the distance from the central maximum to the first maximum. So it's just this distance here. So if we read this graph, we'll notice that it's coming about right there. And that is, let's just count. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 1 centimeter. So that means that if we're coming at the middle of that, then that means that little s is about half a centimeter. So little s is 0.5 centimeters. So I can add that to my list of things that we know. Times 10 to the negative 2. That's what centi is, meters. So now we just have to plug this in and solve for lambda. So the first thing I do is I'll just rearrange this equation solved for lambda. So that means lambda is going to equal to, we just got to rearrange things. So we'll multiply the little d to the other side. So s little d, and then divide the big D to the other side. So now we just have to plug everything in. So we're going to have a separation, a fringe separation of 0.5 times 10 to the negative 2, a distance between the slits of 4.2 times 10 to the negative 4. Remember, that's the little distance, divided by the big distance to the screen, which was 3.8. Okay, if you guys have a calculator, you should try throwing these numbers in there. I'm going to grab my phone and throw my numbers in there, and I can see if I get what you guys get. Are any of you guys doing it?
My calculator is loading.
Okay, loading.
I'm not bothering to go to my room to get my calculator.
Oh, okay, that's fine. If anyone gets it, just shout out the answer. I've already got it.
(5.52 times 10 to the negative 7).
That's what I got. And then what's the unit? I guess I didn't carry over all the units over up through all this stuff, did I? Oh, they're just all meters. You got meters, 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 and so the meters there are going to cancel, leaving it just with meters. So that's the wavelength of the laser. What did it say? Did it say it was a red laser? No, it didn't even say what it was. I think that's red. Red is usually around like I think 600 nanometers or something like that. So just notice that we usually express it in nanometers. Nano is 10 to the negative 9. So if we wanted to, divide this by 100, so if we divide this guy by 100, but we don't want to change the measurement of the wavelength, then we need to multiply the front by 100. So if we divide by 100 to make that negative 7 to a negative 9 so that it's a nanometer, we then need to multiply the front number by 100. So that would give us a wavelength of about 550 nanometers. So generally for visible light, we'll use in the hundreds of nanometers to be visible light. That's it. That's all I have to show you guys today. So I'm 2 minutes early, so if you guys have any questions, you can let me know now. Otherwise, we'll just end it here. So since we got time, we'll look back over the main objectives for today. So interference was first demonstrated for light in 1801 by Thomas Young. It was the Young double-slit experiment. I'm going to be posting a video on the classroom. I strongly recommend you guys check it out. I'm not going to require it, of course. It's a really, really good video about this experiment. The second thing is that light passed through a double slit creates a pattern of interference fringes, and that's what we saw in this question over here. This is your pattern, these interference fringes. I just realized I never finished this question. And then the last thing that we talked about was that you can use this data, these fringes, to deduce or to calculate the wavelength of the light. The thing that's also really cool is if you already know the wavelength, you could use this to measure the size of objects. So if you, like last time I talked about diffracting light across a human hair, if you measure the distance between the fringes on the hair, you could actually determine the diameter of your hair, which is really, really cool. So the diameter of your hair would be the little d right there. So you could actually measure the size of a human hair using a laser through these equations. All right, part B, it said, suggest the effect on the fringes of decreasing the wavelength. So if S is equal to lambda d over little d, then what would happen if we decreased the wavelength? So what would happen if we multiplied by a shorter wavelength? You can see the relationship to the fringe separation would make it be what? Anyone?
It's direct, so it would be smaller.
Yep, it would be smaller. So a shorter wavelength of light will give you a shorter fringe distance. So if we switched out this light for purple light, then those fringe spacings would get much, much shorter. And then the last question said, what's the feature on the graph? So what feature of the graph says that the slit width is, wait. It says, state the feature of the graph that enables you to deduce that the slit width is negligible. All right, so if the slit width is negligible, what you'll see is that the intensity won't drop off that much. The intensity kind of stays more or less constant. If the slit width is not negligible, which means that we screwed up in the assumption that little d was much, much bigger than big D, then you'd end up seeing things like up here where it's it drops off drastically low like this. So in this case, the slit is a much larger distance, and so we got like this way bigger drop off. So this is where it's not negligible. So little d is not negligible, but down in this graph, little d is negligible, since the intensity stays more or less roughly constant. Okay, that's it. I'm done, guys. Have a great day, and I'll see you later.